In 1859, Bernhard Riemann presented a seminal paper on the study of prime number distributions. In it, he asked if the zeros of the zeta function always had a real part of 1/2. In 1901, von Koch proved this was equivalent to the absolute worst error between the prime counting function pi of x minus the log integral at x is absolutely less than the form that he specified, the square root of x times the log of x, basically. Von Koch's estimate is a worst case. That is, the worst the magnitude of separation between our prime counting function pi of x and the log integral at x, while still allowing the zeros of the zeta to have a real part of 1/2. A little exploring will show the reader that if the primes do indeed use the entire range he specified, Legendre's conjectures such as Legendre's prime conjecture could be false. That is, the geometry of the primes is still poorly understood, unless you know this. In 2012, we proved unconditionally and by construction that the absolute worst error between the prime counting function and the log integral at x is absolutely bounded by the square root of x over log x. That is, it's much better than expected. Or more precisely, if m is an index on the primes and Pm is the current prime, then the absolute worst error of our error function at the next prime squared is less than or equal to our index. Note the equal sign. This can also be written as follows: the error at x squared is less than the log integral at x, which is actually a really beautiful form. You may be pleased to note that the actual bounding limit also proves not only Legendre's prime conjecture, but also proves conjectures by Polignac, Hardy and Littlewood, Oppermann, Brocard, and others. That is, given the Riemann hypothesis, which is true now, using von Koch's estimate, the worst the deviation of pi of x from the log integral of x can be rewritten as follows. Here we're bounding it between -1 and 1, trying to normalize it. Rewriting this in our model of prime squared, which is where we sampled the primes, we get the following. And we should expect this that whatever this is, it should occupy a large part of the curve if that's what it says it is. And the following represents the plots through primes of the first 140,000 primes and squares. And we should see something, and we do, but it's not right. Now, we know it should only occupy the bottom half of this curve, or of this plot. But it's getting squashed down to 0. We know now this is a substantial overestimation. And here we're going along, and you can definitely see that what is in between the less than and greater than signs is getting squeezed down to 0. Here we're at 140,000. The von Koch estimate is clearly too high and compresses many distributional features. Our model, however, on the next prime squares being bounded by the index, does not. We also do the same experiment as we did above. We get something between -1 and 1, but now note the equal sign. When we plot the above for the first 280,000 primes, we get a beautiful surprise. We find we used the right looking glass and held it just so and had a, oh, so that's what we're looking at moment. It's all becoming clear. Unless you're watching this from the distant future, the spooky year of 2014 or beyond, in which case this is all obvious. But to us, it's still really cool. And here we are. I mean, behold, this is occupying half of that square. And moreover, look, it's oscillating about -1/2. That's like, wow, who ordered that? Very noisy at the beginning, getting less noisy as we age, or the index increments. Remember, this is on the index. Looking back at von Koch, there's no relationship. This is, it's not wrong. It clearly bounded. Like his estimate was right, but it's not the right answer. This is the right answer. And you see, there's it seems to asymptotically reach this average of 1/2 very quickly within the first 2,000 primes, maybe 4,000 primes. We're at 1/2, and it stays on that, and it will stay on that forever until the next skews number. So here we're at 70,000, and you see it's getting much cleaner and being dominated by longer frequencies. That is, there seems to be a middle range of frequencies that's not allowed. You know, even a blind electrical engineer will tell you where the Fourier spectrum of this is a random matrix. Now we're at 105,000, and it's -1/2 everywhere. It goes up to -0.2 and below -0.8, but almost never. So here, 140,000, 175, 205. This is what seems to be the longest excursion from -1/2 that we've seen. And even here, it barely seems to touch this -0.2 sort of soft hard stop. And it takes quite a huge range of indices. But it does come back to -1/2. So now let's look at it quickly. And you see it getting smoother. Notice the distinct oscillations about -1/2. In asymptotic terms, this line is the log integral at our next prime squared, subtract the log integral at our current prime by 2. Or in old speak, it's the log integral at x, subtract the log integral at x by 2, or the square root of x by 2. Now let's look at Riemann's prime counting function and see what we can understand. And lo and behold, every term makes sense now, except that last term, that's the summation over the zeros of the zeta. We can rewrite this as our error function term, our pi at x minus the log integral at x, as approximately equal to minus the log integral at the root of x over 2, which we call the subspine, and this oscillatory term, the summation over the zeros of the zeta. That is, we can unconditionally squeeze the magnitude of that term in the following bounds. And this maybe gives a hint as to why pi of x oscillates about half the square root as it does. However, our constructive framework for the proofs, called the S model, is random valued and unbiased between the bounds. This while pi of x seems stuck around some lower attractor. In 1914, Littlewood proved that pi of x crosses the log integral infinitely often. These crossings occur at what are called skews numbers, and very little is known about them, except that they are huge. The best estimate for the smallest example is massive. It's 10 to the 316 blah blah blah. We think a deeper understanding of these numbers and their distributions will lead to a deeper understanding of number theory. Our model, as we said, predicts an infinite number of crossings in the sense that it is an unbiased random model in which the log integral is the current expected value of pi of x. It should spend as much time above the mean as below on some scale at least. That's what random functions do. That's the definition of average. However, it makes no assumptions on the frequency of crossings except that it's random valued and the expected long-term average should tend to 0. Let Sk sub n be the nth skews number, and for convenience, set Sk sub 0 equal to 1. That is, we'll artificially say there's a skews crossing at x equals 1. Let psi of x equal our error function at x squared. We were able to show this by construction is legitimate. But we'll call this our error function and say it's a function of x. Let f at n and g be our averaging function, where n and g are integers. And what we're doing is we're summing our psi that's been normalized against its bound, bringing it between plus or minus 1. And we're summing it in between long ranges of skews numbers. N is the start skews number index, and G is the range. We conjecture that given any positive epsilon less than a half, there exists a capital N such that the absolute value of our averaging function is less than epsilon for all n larger than our capital N. We have no idea how large this n, capital N, need be. Perhaps in the millions, or scales of skews number squared, or in the tens. We don't know. This, while on the scale of single skews increments, we would see our averaging function approximately equal minus a half or plus a half, depending if n is even or odd. For example, in the human realm, what we call the human realm, where we can compute, is much less than the first skews number, so we're seeing minus a half. Geometrically, this is what we mean. The black line is the log integral. We also refer to it as the backbone of the primes. That is, we showed constructively that the log integral is the expectation of pi of x. The blue lines are the plus and minus log integral at the square root of x. That's the bounding functions. The red lines we refer to as subspines are our plus and minus 1/2. They're the plus and minus the log integral at half of the root of x. And here come the primes. You see, they linger around one attractor and then spontaneously jump to the next attractor and then return. And we believe they'll do this forever. And moreover, the changes between them will be random as well. If we consider multiplication on the reals, the equation a times b equals c has infinitely many solutions for each c. Restrict multiplication to the integers, and you have at most a finite number of solutions. We think the primes are the result of the quantization of multiplication. That is, somewhere there should exist a quantization operator that takes us from the reals to the primes. To learn more, Google multiplication modulo n along the primorials with its differences and variations applied to the study of the distributions of prime number gaps. Thank you for your time. We hope this was interesting.